but the likelihood that such a question could show up on your exam, right? Like based off of difficulty. In fact, I had another set of questions here that I had to remove because I was asked to remove them because they were too similar to what's on your exam.
Did you post them?
No. So I won't be able to. I can't reveal what those questions are, but if those questions were here, they would be around question number 2 and 3, right? Not conceptually, difficulty-wise. Cool. So now you have a lot of time. I'll give you guys some time to read this, and then we'll take it up. By the way, I'm going to post these solutions on Piazza, so you don't have to write anything down. I want you guys to just sit and think and understand, okay? No taking photos, nothing. Phone away, stop watching that Asia Cup game. And then, oh, by the way, have we started recording? Oh, sorry. Yes. Yes. Try to solve these. Hey, Anaki. Does my hair look good? Okay, let's take it up. Part A, of course, not the NP completeness. What is our certificates? Anyone? Free marks? Yes.
Set of V over 2 nodes.
Yeah, it's a set of V over 2 nodes. Amazing. What's our verifier?
Making sure 1 and 2 has an edge, and 2 and 3 has an edge, and then 3 and 4 has an edge, and okay.
Yeah, just check it's a simple path, right? Just like last time, one extra check before, because the verifier is independent of the certificate. Make sure there's V over 2 nodes, right? At the very start. So that's correct. I'm going to shake this up so you guys get some other flavors. There you go. No more? All right, good. Today's Diabetes Awareness Day. No, it's not. So our certificate is a path in G of size V over 2, which is trivially polysize in G, right? It's just a subset of nodes. I also specify the size just in case. And your verifier checks that there's V over 2 nodes. So you have to check if the length is this is constant time. Then you check that C makes a simple path in G, which is just the size of V over 2 actually, but I just removed the constant. If any of these two checks fails, this is just like a constant. It's just like ordering of things, like if check 1 fails, reject. If, and then nested inside it, do check 2. If it fails, then reject. And if both checks pass, accept. The verifier itself is polytime because V is polytime in G. That's it. That's all you need. Okay. How do we prove that it's NP hard? What would our easiest reduction be? By the way, does anyone see why it's called a Tonian path? It's half of Hamiltonian. That should give it away, no? Okay, what's our reduction? Yes. Oh wow, crazy. Yes, you can use a Hamiltonian path. Yeah. Correct. What do you do though?
So for the S&T path, you can just extend it by like the amount of nodes until the number of nodes double.
But do you make connections? What's the extension?
So you kind of just like stack those on top of like the S&T nodes until.
You don't know what the S&T is.
Oh, never mind.
Oh, okay. You know the S&T, but you don't know what the path is.
So like you know how like the kite problem has a tail?
Yeah. So do it for every node, is what you're saying.
Yeah.
Yeah. Okay. That is correct. But you have to make sure that you're not adding any extra edges between the new nodes and the old nodes. Because if you add edges between the new nodes and the old nodes, you might inevitably end up making a Tonian path in the modified graph. So, yes?
Can we add like isolated nodes, double number of nodes in the original graph?
Yeah. That's exactly it. You just add a bunch of useless nodes, right? How many? As many as there were already in the graph, right? And once you do that, what do you have? You have, if the original graph was of size n, has n nodes, this new graph will have 2n nodes. And whatever was a Hamiltonian path of length n is still a Hamiltonian path, but it's half the number of nodes in this new graph, right? So that works. Here's your candy. Here's another way that you can do it. Okay, I've written something very, very elaborate. But all this is saying is I'm taking the graph and I'm taking a copy. And that's it. And this graph and its copy together make my new graph. Now, if there was a Hamiltonian path, since the number of nodes have doubled, it's a Tonian path. And if there is a Tonian path in the new graph, because the two copies are disconnected, the Tonian path must fully lie in one of the two copies. In fact, it will lie in both because they're copies of each other, which guarantees that it's a corresponding Hamiltonian path in G. Does that make sense? Cool. And that's exactly what we're going to show in our reduction 2. So if G has an undirected Hamiltonian path, notice that this time I'm not even doing ST, right? This is not specifying ST is still NP complete. Then there's some simple path P. By construction, the same P is a simple path, but now the number of nodes have doubled, so now it's a Tonian path instead of a Hamiltonian path. Other way around, if G prime is in Tonian path, so there's a simple path of size V prime over 2. By construction, G is disjoint, so one of the path must fully lie in one of the copies. And the size of the copy is also V prime over 2, which makes it a Hamiltonian path in the original graph. Cool. Questions? Yes?
You have to double the nodes? Because question asked that is there something called at least V over 2, but if it just keep the
Does it still say at least?
at least, yeah. You just keep it as V and you don't even have to double it.
Okay, but then how do you prove the backwards case? If you keep the graph the same. Okay, great. Cool, question number 2. This is really nice. Uh-oh. Need to make very precise movements. There we go. I was trying to eat healthy, but I guess it just doesn't want me to eat healthy. The universe is giving me a sign. NTM, anyone? Okay, if this was a certificate problem, what would we do? Just a truth assignment, right? How can we efficiently write out a truth assignment? Let's say the formula has n variables.
Let's say like NTM stores with the K has n bits.
Mhm.
So one means so if the s position set into 1 means the variable xi is equal to true.
Mhm.
And we guess a set of
All n strings.
and a string that have how much k that is set into 1,
Mm-hmm.
and to verify that it is a satisfiable stuff.
Mm-hmm. Small thing. You cannot, in the NTM, force anything. So you cannot say, let the NTM guess a string of n bits with only k ones in it. You have to do it for all n bits. You don't have the option there because you're generating things. But that's fine because in the verifier section, in the check, you can just check if there's k ones in it.
Let's say so find the computational path that has set by n stuff to true and accepted.
Mm-hmm. That's correct. The only thing that's different from a certificate verifier and an NTM characteristic, for the purpose of this exercise, is instead of the certificate, you're guessing it. But once you're guessed that string, you can just treat that as a certificate. In fact, so much so that I have made a verifier here too, and my NTM just calls the verifier. So it's literally the same thing. Is the NTM just sort of like a wrapper, and sort of try to relate this to what you saw in question number 1. So in my NTM, I have my input phi k, and I suppose v is x1 to xn in some order in phi. So in the order in which they appear. I write all strings of n bits in parallel, so every possible combination, every possible truth assignment. Notice that this is an NTM, so I can do this in linear time, O of n. For every such quote-unquote truth assignment, I pass it to the verifier. And if the verifier returns, I know that for this particular tau, it's true. So there exists some truth assignment, so I can just accept the input. Otherwise, I reject. What does my verifier do? It checks that tau has at most k bits set to true.
Are you going to post this?
Yes. I said this before. Don't worry about taking photos. This will go up immediately after this review seminar. So you check tau has at most k bits, and you check tau satisfies the formula, which you can do by just like plugging in, right? It's a linear time. And then this is identical. Not only this, every single sentence after this is copy pasted, because that's all you need to do. I've just changed the language. Try to use this. This is a neat little trick. It is obvious, so you don't have to get into the nitty-gritty, right? You can just write, like, for the most important steps, you can write their runtime and then say, obviously, whatever, polytime, right? Because if you become too precise and you make a mistake, you might lose a mark. So sometimes it's better to feign that you know, but I'm not going to tell you that I know, right? Cool. So proving that Stingy SAT is NP hard, and actually I'll just say this. Notice that Stingy SAT is a generalization of the SAT problem, right? How is it a generalization? It looks sort of like a special case. No, SAT is literally Stingy SAT, where k is the number of variables, right? Does that make sense? In SAT, I'm allowed to have up to n variables set to true. So if I just set my k to be the number of variables, I would get SAT. So if Stingy SAT was in P, then SAT would be in P. So that's a very simple counter argument to show that Stingy SAT is NP hard, right? But let's actually do a reduction. By the way, I didn't ask you what language to reduce from, but hopefully here everyone was like, yeah, SAT. Yeah? Okay, great. So what's the reduction? It's literally what I just said.
Formulas are the same, and you just set k to the size.
Yeah, the number of variables. That's it. It's literally the same thing that I said. Wait, no candy. Or maybe okay, maybe your preference changed.
No, already.
Okay. Okay. So that's exactly what we're doing. We're keeping the formula the same, and then I'm setting k to be the number of variables. That's it. What's the correctness? Oh, it's very simple. If the formula is satisfiable, and there's only k variables in phi, so tau cannot have more than k variables, so then phi prime k is just as well a Stingy SAT instance, yes instance, right? Okay. The other way around, if phi prime is in Stingy SAT, then there's some satisfying truth assignment with up to k variables. Well, whatever that truth assignment is, it's a valid truth assignment for SAT. So you don't have to think too much. Pretty easy, right? Nifty. Cool. Questions before we move on? No? Great. Anyone here from C73? Sorry. Yes, this was on the final there as an LP problem. Okay. What is our certificates for this problem? Yes.
Certificate just like the n values.
The n values in the table?
No, I meant like the permutation.
Right. Yes, it is a permutation. Correct. So your certificate is the permutation that gives you that optimal whatever greater than equal to k score. What's your verifier? Well, first it needs to check that you have the size. Then it needs to check that it's a valid permutation, and then it needs to compute the score, and then it needs to check if the score is whatever at least k. And then if all of these checks pass, then it's a valid certificate. Otherwise, it's not. Right? Do we need to do anything else? No. And we also have the formula for the score, and so we don't have to think too much. So certificate is the playlist a permutation. If there's n elements, log n bits to represent 1, so a permutation is n log n, right? And then you have these checks. You check it's a permutation, you check if the score is at least k, and that's it. All of this is O of n. Questions? Any questions? No questions. Cool. This is a little bit harder now. How do we show it's NP hard? What's our reduction? Here's my hint to you. Where else do we see a permutation? Okay, but our score is something like this, right? 1, 2, then 2, 3, then 3, 4, 4, 5, whatever, n minus 1, n, and then n to 1, right? Sort of a cycle, right? Okay, so what language should we be using?
Traveling salesman problem.
Okay, that's a very, very good first guess. There's a few issues with the traveling salesman problem. So let's start with the first one. In the traveling salesman problem, we're not looking for a path with greater than equal to k. We're looking for a path that's less than equal to whatever, right? So there's an inequality there. I think we can still manage that somehow, right? We can sort of perform a modification so that that less than equal to becomes a greater than equal to, right? Here's another problem. In this, my playlist T only has values between 0 and 1, right? But my TSP has no constraints on what the edge weights are, right? That's still manageable. You'll have to take the largest weight and then scale everything down, and then now you have everything between 0 and 1. But you see there's a few extra steps that need to be done to make that work, but it will work if you end up doing it. What else can you do? What does traveling salesman come from?
Hamiltonian cycle?
Hamiltonian cycle. So why not just directly do it from Hamiltonian cycle, right? But Hamiltonian cycle doesn't even have weights, but T has like values between 0 and 1.
Can we label if there's an edge, we set it to 1, but if there's no edge between this one and that one, we set
Yep.
it to 0?
Perfect. And then what would your required K be?
The number of nodes in that graph.
Yeah, correct. So, by the way, here I do directed Hamiltonian cycle, but you could just as well do undirected. It doesn't make a difference if the matrix you create is symmetric or not, right? So you sort of do this directed Hamiltonian cycle, where if your graph has a Hamiltonian cycle, then and only then your playlist has something. In fact, since the playlist is an n by n, let's say n is the number of nodes, is an n by n matrix, the largest value your playlist could have is n, right? Because everything's capped by 1. So if you do a permutation, best case, everything is perfectly transitioning one song from the next. Even in that case, you have a playlist score of n. So when I set k to be equal to n, and I say check whether or not it's greater than equal to, I just mean equal to, right? So I'm only worried about equality here. So this is what I do. I take the graph, and I either, if the adjacency matrix is given to me, all I need to do is just set that as my t. And if it's not, I have to create it, which is still O of v squared. And k is the number of nodes, so k is size of v. And then you would just return this pair. And the idea is very similar. If there is some cycle, which is a permutation of the n nodes, then the corresponding permutation of the in the table would be having a score of exactly k, which would make it a yes instance of smooth playlist, right? If the playlist has a permutation with score greater than equal to k, which is size of v. By the way, this is not, if I say it's greater than equal to, I can immediately imply that it's equal to, because k is the absolute best you can do anyways for your construction of t. So then every pair in the permutation correspondingly has a score of 1. And how can that pair have a score of 1? Based off of our construction. It's 1 when there's an edge between them. So that means every single pair, including this last wraparound pair from pi n to pi 1, has an edge between them. So the corresponding set of nodes in the graph is then a Hamiltonian cycle. Yeah? Yes? No? Are we feeling okay with this? Cool. All right. Now I'll start giving you guys more time to do this, because things are getting a little bit tricky. Okay, has everyone read the question? Yes? So before we go to part A, there's a sort of like neat use case of such a problem is, given a larger image, I want to find the existence of a smaller image in it, right? And if I could do this polytime, it would be pretty neat, right? Okay, so NTM characterization. Let's forget about NTM characterization. We can just talk inserts and verifiers, and then just modify our certificate so that we just include it in the NTM, right? So what is our certificate? It's some sort of proof that I can reduce A1 to A2. Yes?
The columns and rows you would delete?
Yeah, just like take the sequence of columns and rows, and that's your certificate. And all you have to do is then perform those rows and column deletions, and you're done. And you just, well, not done. You have to compare after A1, this reduced A1 with A2, and if everything's correct, every single cell is okay, then it's a yes instance your verifier should accept. What is the size of our certificate? Do we need to keep it as a sequence? Do we need a sequence? What I'm trying to say is, if I delete row 1 and then column 3 versus column 3 and then row 1, do I get the same reduced matrix? You don't? Why not?
Row 1, column 3.
So row 1, column 3 versus column 3, row 1. If I just change the order. Yeah, changing the order of deletion doesn't change the reduced matrix. So your certificate doesn't actually need the entire sequence. It only needs the set of which ones you're deleting. And you can do this very, very efficiently, sort of like we did earlier in the truth assignment one, where 0 and 1 means, you can set 1 means remove that particular row or column, and 0 means keep it, right? So that's what we're going to do. But we're going to do it in this NTM form. Our NTM writes all strings of M1 plus N1 bits. So the first M1 bits correspond to the rows, and then the next N1 bits correspond to the columns, right? So M1, N1, and then if the first value is 0, that means you have to keep row 1. And if the second value is 1, it means you have to wipe row 2, and then so on and so forth. That's all you need. The runtime of creating this is linear in the size, and then you run the verifier, and the verifier does the work for you. It deletes those rows and columns according to this sequence, I guess not sequence, this string, and then you have to check if it's equal. So deleting this sequence of rows and columns is going to take proportional to, a worst case, proportional to the entire matrix. Why? What if it's all ones? So I have to delete everything. So I have to delete, the entire matrix. And then comparing this deleted matrix with A2, I can just run a for loop over every element in A2 and try to index that into A1, if it's possible to index, of course. If it isn't, you're immediately going to reject anyways. If you have some inequality, you just reject, right? You could, instead of sort of abstracting that thing away, over here, you can say, you can compare this reduced A1 has dimensions M2 by N2 beforehand, right? That would be a constant time check. So you could still do that. Anyways, either case, your verifier runs in polytime because the input has both A1 and A2. And the NTM is deterministic. At least the verifier part is deterministic, right? So that's it for proving that it's an NP. Here's the harder part. This was so tricky that I decided to help you out and I gave you some options. But now with the options, it's not so tricky. You have plenty of time for this, by the way. You have like 5-10 minutes, however long it takes for you guys. Feel free to talk amongst yourself, all right? But don't be too loud. Respect other people's voices too, but feel free to interact. Okay, I am going to interject a little bit now that you've had time to think. You can only reduce from one of these 4 problems, right? So the first thing you should do is identify the best option out of these 4, right? What do we think is the easiest? Is there preference? Anyone that like prefers one over the other? Is there? Yes. Right. And why do you think Clique should be the language?
Take the adjacency matrix of a clique, then like any subgraph of a clique is also a clique. So
Mm.
you remove like one row of the adjacency matrix.
That's smart. That's smart. So following along on the previous example where sort of our smooth playlist was sort of like the adjacency matrix. I like that. That's very nice. And that indeed is probably your best option because your subset sum is just a single array. It's not a matrix, right? So you can't, it's going to be hard to sort of end up mapping and creating a matrix, not let alone two, just one from a single array. Hamiltonian cycle deals with permutations. Plus, we already did a question, so why would I ask you to do the same thing again? So, and the same thing with SAT, I already did a question, so why would I ask you to do it again? But again, SAT is a formula. It's going to be hard to create a matrix from a formula, although it is, there's probably some weird reduction out there that does it. But it's good to see that Clique is the only one that has a graph, and then we can use the adjacency matrix and then look at subsets. And you know that if there's the subgraph induced by a clique ends up having ones on the non-diagonals, right? It's a full one-by-one matrix essentially. Okay, so try to do it with clique. That's it. Go back to work. Okay, guys, how are we feeling? A little bit more time? Yes? No? Maybe a minute or two? Yeah? Cool. Okay. Anyone with a reduction? Yes.
Well, we're going to use Clique, of course.
Yep.
And I think what we can do is A1 can be an adjacency matrix
Yep.
of G.
Mm-hmm.
And then A2 is just a K by K matrix.
Mm-hmm.
That's all ones except for the diagonal.
What's on the diagonal?
Zeros. Or,
Oh.
sorry.
Okay.
Well, I mean, it's the node to itself, right?
Well, that's allowed.
It doesn't matter.
It kind of does. We'll see. We'll see. But that's the right idea. It's the same idea that you provided for justifying that you'd do a clique, is that the subgraph induced by the clique. So if I were to remove all the rows that aren't corresponding to edges or nodes of the clique, I would get a matrix where there could be 0 1s on the diagonal because we're allowing self loops. So we're not preventing it per se. But everything that's not on the diagonal is a 1, right? And it's symmetric. Okay, so that's correct. That reduction sort of works, but we need to somehow figure out what needs to be on the diagonal, right? The problem is if I set it to all zeros and all ones, I can't guarantee that me doing that sort of subgraph induction on the clique gives me that same all zeros or all ones, because what if there's some elements in the clique that are having self loops? Then the corresponding thing will have a 1. Or what if there's a node in the clique that doesn't have a self loop, and if I want to force my diagonal to be all ones. So it's a little bit different. What can we do?
You can just give everything a self loop.
Sure, you can force everything to have a self loop, but then would that make it a clique of size 2? Would that mess with the clique property?
It has to be 2 nodes. A self loop would be 2
Yeah.
nodes.
So sure, you can do that. You can sort of force G to have a self loop, but that's a modification that you're putting on G. You can't do that. You're given a G and then you want to make a T.
Then the adjacency matrix. Well, then we'll make an adjacency matrix. We'll
And
put
then-
ones in all the diagonals.
Yeah, just put 1s on all the diagonals in the adjacency matrix and require your A2 to be a K by K matrix of all 1s. Okay, this works for this direction. There's a problem with the reverse direction, and we'll explore that when we get to it. But let's set that for now. So your mapping from G to K, you have A1 and A2. So A1 equals adjacency matrix of G with 1s on diagonal, right? And then A2 is K by K matrix of all 1s. Okay, then very good. If there's a clique, the subgraph induced by the clique is just a matrix of all 1s. So A1 is all 1s. Perfect. So this direction works. The problem with the backwards direction is as follows. If there is some sequence of removals of rows and columns in A1 that yields this A2, I need to be able to claim that, hey, take the corresponding set of nodes and that will be a clique in G. The problem is, in A1, there's nothing preventing me from deleting column 1 and 2 and then row 3 and 4. There's no relationship between the two. Whereas when we take the submatrix, we remove the same row and column, right? So here's an example that I'll give you. Oh, that's really bad. That's too big of an example. Let's say K is 2, right? Then this would be your A2, right? And you might have a case where it's impossible to get it by removing the same set of rows and columns. But if I were to remove these and then these, I would get that 2 by 2 matrix. But what does it correspond to in removing in the graph? It doesn't, right? Because you're removing nodes 4 and 5, but then you're removing nodes 1, 2, 3 according to the column, but then you're removing nodes 4 and 5 according to the row. It's sort of weird, right? So we need to somehow force that we remove the same value.
Can we use like a special value for diagonals?
Exactly, exactly. And we'll see why having a value that's not 0, 1 works. Okay? So this is our reduction. It's essentially the same thing, but instead of putting 1 on the diagonals for A1 and A2, I am putting, wait, did I just go all the way up? Yeah, I'm putting 63 on the diagonals. The forward direction is identical, right? There's 63 on the columns, you're fine. The backwards direction is now very, very easy. Because if you have some sort of sequence of removals that yields a A2 that has 63 on the diagonals, it forces that if you remove a row, you have to remove its corresponding column. Why? Because if you remove the row and not its column, there's no 63 in that column. So there's no way you're making A2 because A2 has a 63 in every column, right? So that sort of links these two indices, the rows and columns together. So this is our arguments. The forward direction is pretty straightforward. So suppose you have a clique, then the subgraph induced by the clique has an adjacency matrix with 1s on non-diagonal elements. So in A1, you still have that 1s on non-diagonal elements, and then you're forcing 63 on the diagonal. That gives you exactly A2. That's your matrix. Okay. The other way around, if there's some sequence of deletion that gives you A2, 63 appears on the diagonal, so it appears once in each row and column. That's it. Only once. So if you delete a row, but not the corresponding column, that column will be left with no 63. But then it's impossible for you to reduce to A2, right? So you know that now if there is some sequence, it has to delete in pairs, row I and column I, right? And now you have this relationship, and then now you can say, okay, for every whatever set of rows that were deleted, we know the columns were also deleted, those set of rows that were deleted, take everything else that wasn't deleted, and that will give you your clique, right? By construction. Okay, how are we feeling about this? This is hard. Would this question show up on your exam? If I didn't give you the options, the 4 options, definitely no. If I gave you the 4 options, maybe, but still pretty unlikely. If I gave you that you have to reduce from clique, if I gave you that at the very start, that you have to do it from clique, then probably there's a 50-50 chance that something like this might show up. Yes?
If it says what reduction we should use, is it like always going to be like the optimal one? Or could it be that they chose a reduction to make it specifically harder?
Yeah, they can. They can. And I think I will force something like that too. Or I won't force it, but I'll show it. In a past exam, they forced something to do, like use like subset sum when partition would have been easier. And we'll see an example like that here. Okay. Questions before we move on? No questions. Great. This is just a lot of work. Let's go. Okay, let's start with part A. What is our certificate? Hint, hint, if at this point, whenever the question is there blank such that blank, blah, blah, blah. The blank part is supposed to be our certificate, right? So in this case, it would be whatever, the subset X. Yeah?
A set of keynotes.
Yeah, it's a set of k-nodes. And what do we need to verify? We need to verify that if I remove those k-nodes, then whatever I'm left with doesn't have any cycles. Can I do that in polytime? How? DFS. Really nice. So your certificate is a set of k-nodes, which is trivially polysize because the graph has all the nodes. And here again, we're assuming k less than or equal to n, because otherwise it's a trivial no instance. We don't have to handle that. Your verifier checks that C contains k-nodes by checking its length. It removes those k-nodes from G and all the edges that are incident on it. That's implicit here. And then it checks that G no longer has a cycle. And this is DFS on this modified G. The number of edges, worst case, the nodes you removed didn't have any edges, so it stays the same. But you have k less nodes, so your DFS is whatever, v minus k plus e. And that's it. That's your verifier. Cool? Prove it's NP hard. My hint to this is, in what other languages, or in what other problems do we select subsets of nodes? Anyone want to list them off? Yes. Clique, IS, vertex cover. Anything else? No? Yes? Exact cover? Yes, sure. But exact cover deals with like a universe and stuff. Let's just focus on its graph problem only, right? Okay. Well, this gives you a good start, right? Now, which of these three problems relates more to the problem at hand? Clique talks about having a bunch of edges versus independent set talks about not having edges versus
Intuitively, vertex cover means choosing edges, choosing nodes so that you cover every edge, right?
yeah, you're covering every edge. But in this one, we need to remove all the cycles. But keep going.
But if you remove all the nodes from the vertex cover,
Yeah.
you end up with basically
You're on the right track. Keep going.
if you remove all the nodes from that, every edge is now missing an edge point. So you're basically deleting all the edges.
Exactly. Really smart. So here's the intuition that was built upon vertex cover. If you have some vertex cover, what does that mean for it to be a vertex cover? Every edge has some endpoint. One of the two endpoints is in this vertex cover. So when I remove this vertex cover from the graph and its edges, not only am I left with no cycles, I'm left with no edges. There's nothing there. It's an empty graph. So that's probably a pretty nice start. Yes, but Hamiltonian cycle deals with permutations, where we don't necessarily have to deal with permutations here, right? We're just selecting a subset. So if you could, but that doesn't guarantee that there's a Hamiltonian cycle. How are you doing a mapping?
True. Only thing is, I'm not sure how you'll go the other direction.
Yeah. So let's try this out as a whole. Let's try to do vertex cover. And the idea is that if you have a vertex cover, the same vertex cover serves as a feedback set in the same graph, right? Because there's no cycles, there's no edges either. But in the backwards way, if there's a feedback set, you can't necessarily say that there's a vertex cover on this side. So you can't let the graph be identical in your reduction. You have to do something else, right? You need to somehow make it so that every edge has like a sort of like a cycle isomorphism in the new graph, right? That way, you know that whenever you remove a cycle here, it corresponds to removing an edge over here. So you need sort of this one-to-one correspondence between an edge and like a cycle in this modified graph. So this is attempt 1. No, more so that your feedback set must contain, for every edge in the original graph, it must contain one of the two endpoints, right? And how do you force that? Well, if somehow that edge has a corresponding cycle which can only be removed when one of those two nodes are in the feedback set. So you could do something like that, right?
Would every pair of edge need to be a cycle?
Yeah, but it's not a cycle, right? You can't have it's just a two-clique. A pair of edge can't be a cycle.
So these are undirected graphs, right?
Yeah.
Okay.
So then you would need to do something else, some modification, right, to make this sort of happen. I think you're on the right track, though. Okay, does anyone have an attempt, a guess? Hint, hint, how can you change a graph? How can you add? Okay, this is a very important point. Whenever you're given some input, when you're doing your modification, it is very unlikely that we ask you to remove or modify the input by changing things in it, right? Usually we'll only ask you to add things to it, right? If you remove things, you're losing information, right? And that's sort of the wrong direction that you're trying to go. You want your reduction to keep all the information of the old thing and have some more clarification. So in this scenario, it would mean you're modifying the graph, but you can't delete an edge. You can't do anything. You can add edges and you can add nodes. And you want to do it so that sort of each edge has a corresponding cycle in the feedback set.
Could we do something like, when we added a tail to every node?
Yeah.
For every single node, we add 2 new nodes that make a cycle with that one node.
Yep, and that, okay, but then, sure, we can start with that. So the suggestion was take a node and then make a copy, you left, you right, and then make this connection. But what this would force is their feedback vertex set would have to have every single thing in the cover. Yeah.
For every edge that exists in the original node,
Yeah.
you add another node that connects to both parts of those edges of that edge. For every UV that has an edge, you add a W like that.
Better. Now you're relating an edge to a 3 cycle. Everything that had an edge now has a corresponding 3 cycle in this modified graph. So when your feedback vertex set, if a feedback vertex set exists, it must contain one of these 3. But doesn't mean it contains one of these 2, which is actually what we want. That's an argument that we'll postpone, right? But let's try this. Let's do this reduction. So all I'm doing is for every edge, UV, I'm adding a new node XUV, and I'm connecting it to both U and V. So now for every edge that existed, there's like a 3 cycle. Okay, and I keep K prime to be the same as K. Now forward direction is very simple. If you have a vertex cover, that same vertex cover acts as a feedback set here. Why? Anyone? Because if it's a vertex cover, then for every edge, UV, one of U or V is in it, which means if I remove that, I am removing this edge. I am also removing this edge, right? So I'm only left with like pairs like these. Additionally, we already talked about it. The vertex cover, all the edges in the original graph, they're all gone. So you're left with something like this. You're just left with these like pairs that are not connected. So there's no cycles at all, right? So that's the forward direction. If you have a vertex cover, then for every edge, one of the two nodes belongs in the cover. I've written out the cover to UT1 to UTK. This T1 to TK are just subscripts. I can't say U1 to UK. There's some subscript of K nodes. So the subgraph induced by removing them has 0 edges. So the corresponding subgraph of G prime by removing that same cover only contains edges incident on the XUV. Only contains either this or this. In fact, it can only contain one of the two, right? Since a cycle requires its node to have at least 2 edges, and XUV only has 1 edge, it's impossible to have a cycle. Make sense? Great. This is sort of why we wanted k equals 2 separately in the kite problem, right? Because you want, like, if it's a cycle, you need at least 2, right? So you need to make sure if it was part of a clique, you need at least 2 again, and it's the same arguments. Okay, backwards case. This is a little bit hard. If there exists a feedback vertex set, what can we say? We know there's triples for every edge. So we know one of the 3 has to be in an X, right? So U in X, or V in X, or XUV in X. Let's delete this. Okay. But we can't say this X is a corresponding vertex cover, because what if XUV was an X? There's no XUV in the original graph at all. So we can't say that this is correct. What do we need to do? Can I claim that it's fine to not have XUV here? Can I claim that I don't need XUV? From X, I can create a new X prime that doesn't contain any XUV nodes. Can you make that happen? Here's the question. If XUV is in this feedback set, what's it preventing? What cycles is it preventing? It's literally this. This is the only cycle that XUV prevents. So I can just remove it and instead substitute it with one of U or V, right? And if U or V already exists, then I don't even need it. I have an even smaller feedback set. Is everyone following along why we can remove this? The only cycle that's being provided by this node is this 3 cycle. If I were to just substitute it with U, I would still be preventing this cycle, plus I have the chance to prevent a lot more, right? So I'm always doing better. And since I substituted, the size didn't change. Additionally, if the X already contains one of U or V, then I don't even need XUV. I can remove it and make an even smaller feedback set. Cool. So let's recap this. So suppose you have a feedback set, X. Note that for every edge, at least one of them must belong to X, otherwise you'll have a 3 cycle, right? And we know feedback sets don't have 3 cycles after you remove those nodes. Also observe that if X contains some XUV, then you can remove it or replace it with UV, depending on whether or not U or V exist in X. Because XUV only prevents this 3 cycle, which either already is being prevented if U or V is already in X, and if it's not, can be substituted with one of the 2, right? So without loss of generality, you can assume that if there exists a feedback set, there exists a feedback set with just nodes that belong in the original graph that don't contain these XUVs, right? And now it's very easy to see that, okay, great. Now these set of nodes are a corresponding vertex cover in the original graph, right? Does that make sense? I said if this is the case if there exists X such that for all UV, this statement is true, then it implies that there exists some X prime such that for all UV, I only need one of the two, right? I can get away with one of the two. So U and X prime or V and X prime. Is this not exactly the definition of a vertex cover? For every edge, one of the two endpoints has to be in it. So this would make it a vertex cover. So X prime would be a corresponding vertex cover in G. Cool. Questions? No? We're going to be running a little bit over. Do you want to do that, or do you want to end early and then try and do question 6 on your own? Do we want to take a look at question 6 before you guys decide that? Let's take a look at question 6. Okay, has everyone read the question? What's the language that we should reduce this from? Yes, that's perfect. So we know we have to do partition. It's in the name. But partition wants to put it into two equally, whose sums are equal. In this case, you want like 1 to be the square of the other. You want like 10 and 100. You want like 4 and 16, right? So what do we need to do? It's a little bit tricky. We need to somehow take in an A, which is in partition, and create an S, which is in square partition. Remember I said it's not a good idea to remove or modify. It's always a good idea to add. So that's probably the hint you want. OK, do you want to solve it here or take home? I'll do a raise of hands. Take home. Solve it here. Great. Great. So then figure out. OK, so let's speed through the certificate verifier. What's the certificate?
The sequence, the subsequence.
Yeah, just give me S prime. That's all I need, right? And what do I need to verify? I create the partition according to the sequence, and then I add up one and I add up the other, and then I make sure that one's the square of the other, and then I'm done, right? So which one's the square of the other? If I give S prime, I take the sum, I call it K, and then I take S over S prime and I call it Y, then K needs to be equal to Y square, for example, right? And that's all you have to do. It is obvious that this the checks in the verifier are polytime, and that's all you have to argue about. This is an NTM characterization, so instead of the quote-unquote certificate, you want it's as a guessed string. Just like last time, we don't need the entire sequence or the integers. We can just have like a bit string that corresponds to the subsequence, right? So if there's 10 elements, I have a 10-bit certificate. Cool. Square partition is NP hard. Start solving. Go ahead.
You just add k over 2 squared minus k over 0.
What's k?
Oh, I'm assuming k to be the total.
Right, right. Okay, correct. Let's not use this then. K is the, let's use t as the total. Sigma of A is equal to t. So you're saying add, let k equals t over 2. And you're saying k squared minus k? Okay. And so if there's a partition there, what would you have here?
The partition in A?
Yeah. So you have k and k. Sums up to k, sums up to k. How are you, with these two elements, which one goes where?
Doesn't matter. You just have one left.
Yeah.
K squared.
One of them just becomes k squared. Okay. What about the other way around?
You just remove k squared minus k.
But from where?
Doesn't matter.
How do you know which one's k squared? How do you know which one's k squared minus k?
How do you know which one?
Yeah. Like you have S, and you know you have to remove one element, and then you have a partition. But which one? How do you know which one's k squared minus k? Little tricky, but you're on the right track, right? So you need to add elements to make it work. And this was a really good attempt. This would gain you like, whatever, more than 50% of the marks, even if you just left it like this. I will show a harder reduction. I will go from subset sum when I don't need to. But subset sum is a generalization of partition, right? If you just set k to be t over 2 in this reduction that I show you, you will exactly get the partition reduction, right? So it's a little bit harder, but it gives you an easy way to check whether your partition reduction is also correct. So now let's actually use the k as I wanted to, which I unfortunately gave this out. I'm happy no one noticed. But we want to go from sort of like k and what is this? T minus k, right? To something like y and y square, right? So what I'm going to think of is, assuming there's a partition like that, there's a subset like that with k and k minus t, I'm only allowed to add nodes. So let's say I add some node to the first part and the some node to the others in such a way, in tandem, so that you get y and y square accordingly, right? So what's the idea? Well, here's the trick. So let's say I added to this part, I added beta, right? Some number beta. And to this first part, that gives you the subset of k, sum, or k total, I added alpha. So, and I want that to somehow become y and y squared. So what do I have? If everything I had before plus alpha gives me y, I have a relationship between alpha and y, right? I have k plus alpha equals y, right? Or alpha is y minus k. We don't know what this y is, but alpha is y minus k. Similarly, you have a t minus k over here, and then if you also include beta in this, so this is t minus k, and then I also have this beta in this partition, what do I have? I have t minus k plus beta gives you y squared, right? T minus k plus beta equals y squared, which again then tells me that beta needs to be y squared minus t minus k. Literally pick any y, and you will be able to just substitute alpha and beta, and everything will work out magically. But not exact. Don't pick any y. What do alpha and beta need to be? If I'm adding nodes to S, they should be valid things, right? So what can alpha and beta be? According to the definition of square partition, S is a sequence of positive integers. So then both alpha and beta need to be positive integers. What value would satisfy that for both alpha and beta? It needs to be at least k, well, k plus 1 to make it a positive integer. And then over here, what does it need to be? You need a y squared to be greater than t minus k. But then if you solve for that inequality, you're going to get something very, very stupid. We know that A has positive elements, so the total is positive. And we can assume k is less than the total, otherwise it's a trivial no instance. So then let's just say y is t, or t plus 1 or something like that. Right? What would happen? Then t minus k is definitely positive, and t squared, which is greater than, much greater than t minus k, is still positive, right? So that's what I do. I set, oh, did I just close it? Uh-oh. Control Shift T. What is it? Screw this. Control Shift T. Control Shift T. Hey, there we go. So I set y to be t plus 1, and I set alpha and beta accordingly, right? So it's t plus 1 minus k, and then t plus 1 squared minus t minus k. And I let this S be the union of A and just alpha and beta. The forward direction should be obvious now because I set my values so that I get y and y squared. So those are good. But the backwards direction needs some thinking. In particular, the problem with your partition reduction was that you didn't know which element was the k squared minus k. We need to somehow make it so that we know which element is k squared, the corresponding, which element is alpha and which element is beta, so then I can remove them and then argue about there being a subset, right? So this is what I need to argue. If you have some square partition, so S1 and S2, where the sum of S1 is the square of the sum of S2, so S1 is y and S2 is y squared. So this would be S1 and this would be S2. Let me draw this out. This must be y squared, this is y, this is S1, and this is S2. Right? The sum of S1, y, is the square of the, other way around then. Whoops. Same thing though, right? There's some partition that this works. So we know that S1 sums to y squared, and S2 sums to y. Beta, which was this massive y squared minus t minus k, cannot be in S2. In S2. Why? Well, because beta is greater than y. Right? If I know that this entire partition S2 sums up to y and beta is greater than it, there's no way that beta can be in there. Otherwise, the sum would exceed y. Right? And I show some math for it, but it essentially boils down to y squared minus t minus k ends up being greater than y. Okay, so we know that beta is here. Okay, so what can we say about the rest of the sum? If beta is here and the total is y squared and beta is y squared minus t minus k, what do we know about this part? T minus k, right? So this part sums to t minus k. I argue now that alpha cannot be here. Why not? Because alpha is greater than t minus k. And that argument's a little bit easier. Alpha, we defined it to be y minus k, y is t plus 1. T plus 1 minus k is definitely bigger than t minus k. So then that would force alpha to be in S2. Now I say, just take a look at this. if alpha is here, and the total is y, and alpha is y minus k, what is this region sum to? K. There's your subset sum. This particular one sums to k. Okay? So it required you to figure out where alpha and beta can be in the partition. You could have a very similar problem. Instead of square partition, it is double partition, where you want k and 2k. Or it could be cubic partition, where it's like k and k cube. And you'd similarly just do sort of this analysis. Okay, questions? Yes?
So since this is like the last one, this has a low chance of being an exam, something like this.
Oh yeah, this is pretty unlikely for it to show up in your exam. But you can see, but the correspondingly two-sum might, the double partition might show up. I don't know if you guys know, there was a problem called odd subset sum in a previous year, which sort of forced, it just said odd subset sum, you're looking for subset sum, but k has to be odd. And you had to do a reduction from subset sum. And it involved adding an element and then finding that this element cannot be in this part and continuing from there. Your takeaways from this review seminar should be A, certificate verifier and NTM aren't really that different, right? And B, when you're doing these NP completeness problems, don't do depth first search. Don't find like the first feasible language and then just go all in and then lose time. Instead, have like a broader sort of bird's eye view of, and sort of take some time, stop, think which languages would make it easier for you to reduce, and then proceed. Okay? And if there's any other takeaways, let me know. If you liked this review seminar, you can e-transfer me money. Or you can just go and give me a thumbs up on YouTube. That's it. You can cut it.